Okay, so the next thing after thinking about sequences is thinking about series, and a series is like a sequence, and it's an ordered list, but the series is an ordered list where there are summations between. And so we can think of A0 plus A1 plus A2 plus A3. So each of the terms in the series could be drawn from a sequence, or alternatively, maybe the more helpful thing to think about is to think of the partial sum. So first A0, then A0 plus A1, A0 plus A1 plus A2, and we could call these partial sums. We could make those an ordered list, and that ordered list would indeed be a sequence. 0, 1, 2, and so on. If this sequence has a limit, converges to something, so too does the series converge as the number of terms considered in the partial series goes to infinity. Okay, so now, what are some of the things that we might think about if we think about a series that might converge to something? Well, the terms in the series have to get smaller. If they keep getting bigger, so that A3 is bigger than A2 and A4 is bigger than A3 and so on, there's no way that series is going to converge. It's just going to keep going farther and farther away. So the first thing you might check is called the preliminary test, and that just checks whether each of the terms that's being added is getting smaller and smaller. You can be a little more strict than just smaller and smaller and examine the ratio of an plus 1 to an, so 3 to 2 or 2 to 1 or 1 to 0, but continuing on as we get bigger, this ratio, as the limit of n goes to infinity, had better do something to get converging. If each term, if this limit gives us a ratio r, you can consider whether r is greater than 1. If r is greater than 1, then that means that each term is bigger than the preceding one. So that clearly doesn't converge. If r is less than 1, then that means that the terms are getting smaller and smaller and smaller, exponentially, geometrically fast. They're getting smaller and smaller, and that turns out to be sufficient to prove that it converges. And if r is equal to 1, then you actually have to just go back to the drawing board and try again. And so the ratio test gives us a way to find out when some series, the ones that this ratio goes to a particular limit as n gets big, if that ratio is small enough, then you can guarantee there's convergence. But you also could take a series and compare it to another series that you already know the behavior of. If you can take a cluster of terms and compare them to a cluster of terms in another series and show that they are systematically bigger than the comparison series, and if the comparison series diverges, then so too does the new series that you're considering. On the other hand, if you can say that they are systematically smaller than a comparison series for some n up to infinity, and that comparison series converges, then you can say that the new series also converges. And so you can compare against series that you have a good handle on, and we're going to get to some that we will in a little while, and then you can make sense of that. Let's talk about one particular one which is called the harmonic series, which goes 1, 1, 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 plus dot dot dot. Actually, let's do a few more. 1/6 plus 1/7 plus 1/8 plus dot dot dot. That series has the terms getting smaller in each additional term, but they're not getting smaller by a fixed ratio. 1/2 compared to 1/3 compared to 1/4. The ratios are changing from term to term to term. So we can't use the ratio test to address this. But we could use a comparison test. So let's compare to the following. 1 plus brackets 1/2 plus 1/2. Oops, that's not the one I wanted to do. 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus not that. Okay, so 1 is the same size as 1, 1/2 is the same size as 1/2. But look at this one, 1/3 plus 1/4, that's bigger than 1/4 plus 1/4, because 1/3 is bigger than 1/4. Likewise, 1/5 plus 1/6 plus 1/7 plus 1/8 is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, because 1/5 is bigger than 1/8, 1/6, and so on. Okay, now here's the next step. Notice that every term in square brackets here adds up to 1/2. So that means that our harmonic series is greater than a series which is 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, which is clearly a divergent series. So the harmonic series must also be a divergent series because it's bigger than this diverging series. Okay. A last thing that we want to think about is, what if the sign changes from term to term as we go along? Well, we could have, A0 minus, and let's just write absolute values, minus A1 plus A2 or something like that, minus A3 and so forth, where we're not just adding up the same way each time. Now how do we assess convergence? Well, we could just take the absolute value of every term and do something like the ratio test or the comparison test and say, if the sequence that was the absolute value of every term with pluses in between, if that one converges, then clearly this one also converges because it's going even faster because there's cancellation. This has no cancellation, this has some cancellation. Okay? But if that fails, you could think, well, what if we just collected all the positive terms together and see what they add up to, and all the negative terms and see what they add up to? And if you did that and both the positive series and the negative term series both had a finite limit, then you could actually say that this series does converge to something. But if both of them diverge, this series still also could converge. So you have to be extremely careful. And in fact, that collecting some of the terms over here and some of the terms over there, you can end up having problems where your partial ingredients are all tangled up. So these kind of series are quite hard to manage if they're of a general form. So instead, we're going to only really see these kind of series when there's something special about them, that they're either a geometric series or power law series, where we are going to know more about their convergence properties. Okay, the last thing that I wanted to talk about in series for this was arithmetic, geometric, power series, and just what those are. So an arithmetic series is when you're just adding together numbers. It's like the arithmetic sequence that we talked about, and the difference between the numbers is the same. And it could be a big difference, like these have ones, or it could have twos, or it could have point ones, but each interval that you're adding is the same. That is going to be a divergent series. A geometric series is like this example is multiplying. So we could write a geometric series as a plus a times r plus a times r squared plus a times r cubed plus a times r fourth plus dot dot dot. That series might diverge or might converge depending on how big r is. And so if we use the ratio test on this, we see that the ratio between each of the terms is exactly the same. And so r needs to be less than 1 in order for this to converge. But if it is, then it does. And so that's a really interesting series. We're going to talk a little bit later about what its properties are. And then the last flavor of series that we wanted to talk about was a power series, which looks a lot like a geometric series, but it's really for a function of a variable like x. And it might have different coefficients for each power of x. And those coefficients are to be specified at a later time. The reason why we throw this one in is because this is of the form of things like Taylor series that are going to come out of our analysis of calculus and how we express functions as approximations. Okay, so let's jump back here to the geometric series and see if we can figure out what its limit is. Okay, so how can we tell what the limit of the geometric series is? Well, we can only tell what the limit of the geometric series is if the geometric series actually has a limit. So we're restricting ourselves to thinking about convergent versions, that is, the case where r is less than 1, or the magnitude of r is less than 1. It could actually be an alternating series too. But let's consider what a finite length series is of the geometric series. And that always converges because it has only a finite number of terms. So even if it was doing something crazy, we'd have a finite number of terms. But we're going to head back, because we're headed towards the limit, to thinking about it in the case where r is less than, the magnitude of r is less than 1. Okay, so here is an n-term finite series. So a, ar, ar2, ar3, cubed, and so on up to ar to the n minus 1th power. And that's because we started counting with the first one. So we have 1 extra, so n minus 1. And the secret to figuring out the limit is to compare it to a very close partner series, which is r times the same series. Since it's finite in length, we know that it has a finite value, so we can multiply through and not have any problems. So that one is ar plus ar squared plus ar cubed plus dot 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 ar to the n. This time it's n instead of n plus 1 because we've got an extra r floating around. Okay, so we've got our two finite series, Sn and r times S of n. And now notice that every term in Sn, except for the first one, has a partner in r times Sn, and every term in r times Sn has a partner that's the same in Sn, except for the last one. So if we subtract these two, we get a pretty simple formula that Sn minus r times Sn is just the first term, a, minus the last term, ar to the n. Now, we can do a little bit of algebra and write Sn equals a minus ar to the n, over 1 minus r. Or simplifying a little bit more, a times 1 minus r to the n over 1 minus r. And now you can see why r equals 1 is a funny version of this, because r equals 1 is 0 over 0 in this limit, but as long as r is less than 1, we get something out of this formula, and that something depends on n, but and also depends on a out front. Okay, so that's nearly there. That, remember, that's for the finite length series Sn. What's the limit of Sn as n goes to infinity? That's the question. Well, the limit of Sn is just going to be the limit as n goes to infinity of a 1 minus r to the n over 1 minus r. The limit, a doesn't care how big n is, 1 doesn't care how big n is, 1 minus r doesn't care how big n is, but r to the n surely does care. Now remember, we had to use an r that was less than 1, so the nth power of that, as n goes to infinity, is getting closer and closer and closer to 0. In fact, it is 0, so the limit is equal to a times 1 over 1 minus r. That is the infinite series limit for a geometric series.